Log on, tune in, find out. Another good idea from Cambridge.
Talking about networks.
I'm going to be talking about some very simple networks. I'm going to be talking about distance methods on them. Let me remind you how distance methods are done on trees. So here's an example of a tree. In black are the tips or the leaves of the tree, including, in this case, one up there. And in red are the distances of each of the edges. So how do we, so each edge is assumed to have some kind of a non-negative weight, which measures the amount of genetic change along the arc. And the distance function is additive if you get the distance between two things by just adding all the red numbers on the path. So if you wanted to find the distance between 2 and 4, you look at the unique path between 2 and 4, you add the red numbers, 1, 4, 5, and 2, and you get 12. So that's how those work. Those are nice approaches. There's a bunch of theorems about these things, but most fundamental, suppose no vertex has total degree 2. Suppose you have an additive distance function on the tree t, then the tree is uniquely determined and the weights are uniquely determined, and you can get explicit formulas for the weights once the tree is known. And in fact, there are very fast methods. Neighbor joining is a wonderful method which takes these distances and produces the trees if you're given the exact distances, and it's very robust in the presence of various errors. I'm interested in rooted-directed cyclic networks. So the question is, can any of this be generalized to the networks? Here's an example of a network. The network might have things, vertices like this, which have hybridization events or lateral gene transfers. And we're going to assume that the distances are known between the tips, including the root. The one there corresponds to an outgroup, probably. And in this case, this is my notation for the for 4 choose 2, the binomial coefficient. In this case, there are 6 distances known. The data would be 6 numbers, but you notice there are 17 arcs. And the lengths of these 17 arcs can't be determined from the distances between those things. So the big conclusion is that if there are more arbitrary parameters than distances, the parameters can't be uniquely determined, and so we need to restrict the network. We can't do this for completely general networks. Let's look at a very simple network to start off with. Here's perhaps the simplest network in which there's a hybridization event. Once again, there are 4 leaves. That means there are 6 distances. We're allowed 6 numbers. And if you count, there are 8 arcs. So it looks as though this is going to be a very short talk. Now notice there was one hybridization event. And so I call that hybrid. I call these other things are tree children because the tip of the arc is placed within degree 1. So how can we get down to 6? Well, I notice there are 2 things there. They're special. There are the arcs that go into the hybrid. There are 2 arcs that go into hybrid. So I'm going to assume in this talk that the weight on an arc which goes into a hybrid vertex is going to be 0. If I do that, notice that I have 6 distances and 6 parameters. So at least mathematically it's good. I can do arithmetic. Now, is this plausible? Well, I'm thinking of this as saying when this hybridization event occurred, some genome passed intactly to 7 from 6 and some intactly from 8. So what's being measured is mutations along arcs. Something was intact there. So this is an instantaneous occurrence. And so it's not implausible to use the number 0 for those weights. So for the remainder of the talk, I'm going to assume that each arc has a weight, which is non-negative. But if the end is hybrid, then the weight is 0. And I'm going to assume that each hybrid vertex has exactly 1 child, as here. Now, is there a reasonable, biologically plausible way to try to get a distance from this information? Well, if we're given a network like this, which has these 2 hybrid vertices, various genes are likely to follow different trees displayed by the network. So there's a network, but there's one of the trees that's actually displayed. And plausible that biologically what's happening is that for a particular gene it's following one of these trees. Okay, how would I define these trees formally? Well, parent map is a map which gives for every vertex its parent, except you don't try to do it for the root. So a parent map is a map which takes a parent. The set of all parents is P of the network. So for each parent map then yields a particular tree. So if the network is n, then I write n sub p for the tree that's obtained using that parent map. So if the parent of 19 was 22, and the parent of 16 was 17, it means the parent of 19 was 22, the parent of 16 was 17. So I throw out the other things. I'm using every parent. There's a tree. So that's what the notation is. So here's the main definition. This is the take-home thing to think about in this talk. Suppose you have all those parent maps. What I'm going to call the tree average distance is found by doing what? You take each NP, each parent map, you find the distance using that parent map, and then you take the average. So you're averaging the trees. So let's show you how this would apply. Suppose we want to find the distances between 1 and 2, and between 1 and 3. Two different examples. Well, in this particular case, there are just two parent maps. So if we chose the parent map where the parent of 7 was 6, then you're left with this tree with those red numbers, those red weights, and you can find the distance. The distance between 1 and 3 is found by 3 plus 1 plus 0 plus 2. So it's 6. Oops, sorry. The other tree from the other parent map is this one. You can similarly find these things. How do you find the tree average distance? Well, you add together the numbers. The distance from 1 and 2, both cases were 7. The distance between 1 and 3 in the two different cases were 6 and 9. So here we get the average. That's the tree average distance. So it's an easy thing to do. It's possibly biologically plausible. Okay, so let's just look at some fundamental properties of these things. Suppose that each tree child has positive weight, and suppose each leaf is a tree child, then the tree average distance is going to be a metric. So you certainly get a metric out, and in fact there are other conditions in which you get a metric. So the major questions is suppose n is given and the tree average distance is given. When are the arc lengths uniquely determined? When is the topology uniquely determined? Well, for the first one, on small examples, it's pretty easy to do. You can form a vector which is all, if you know the network, and you have a vector, a W consisting of all the weights on the arc, and then you can have a vector consisting of all the distances between the various tips, and this is a linear transformation. There's a matrix M which is between them. So if you can see whether that the arc lengths are uniquely determined, provided that this matrix has null space 0. So that's an easy thing to do for small examples. If you find the matrix, you can ask Mathematica to do it, which is what I do. But there's some complications. Here, for example, the numerical restrictions are fairly reasonable. There are 10 normal arcs. 10 arcs, so it's 10 free parameters. And there are 10 distances, so I choose 2. But the arc lengths are not uniquely determined, even then. So there's a relationship, and it's a complicated relationship involving 7 arc lengths. So you need to have some other kinds of restrictions. Okay, so here's one kind of thing. An arc UV is redundant if there's a directed path from U to B different from the arc. So if we look over here, in this network, 6 to 8 is redundant because, hey, there's another path from 6 to 7 to 8, which is in there. So in some sense, the 6 to 8 is giving redundant information in terms of the gene flow. Now, the very curious thing, here we start with a tree. Trees, the distances are uniquely determined. You change it in a simple way so that there's a redundant arc, and now the arc lengths may not be uniquely determined, even though there are enough parameters. You have 6 normal arcs and 6 distances, but the ways to divide, there are bunches of ways to divide the distances. So redundant arcs are problematic. Now, those of you who have heard other talks know I often talk about things called normal networks. A network is normal for this talk, provided there are no redundant arcs. You're going to have to throw them out. And whenever you have a vertex that isn't a leaf, there's a tree child, a normal vertex. So, and of course, every hybrid already has a tree child. So this is an example of a normal network. This is an example of a network that's not normal. It's not normal because you look at this particular vertex, it doesn't have a tree child. Both children are hybrids. Okay, I like normal networks because they're a fairly simple, perhaps toy system. If you have a normal network and there are n tips, then there aren't very many hybrid vertices. It's linear, at most n minus 2. And there aren't that many vertices. It's quadratic number of vertices, and really there aren't that many arcs. So these are simple networks, possibly the kinds that we might understand biologically rather than the big, horrendous, complicated things. Okay, now here's another sort of fundamental thing. If you had a normal network, then the trees are all distinct topologically. So you might be saying, the name that I gave to the distance is wrong because it was the parent map average. But in fact, if you look at the set of trees, all the trees are distinct. So it really is a tree average because you get the same number by adding together the distances on the displayed trees. Okay, what's the main theorem of this talk? Okay, suppose we have a normal network. We have the tree average distance. And suppose that we have the other standard distances. Then, and you know the network, and you know the tree average distance, but you don't know the arc lengths. Then the arc lengths are uniquely determined. And in fact, there's a simple way to find out what those numbers are. So this is an example. I'll show you how it's done in this particular case. As a corollary, there can't be that many normal arcs that lead into something because you can get it from n choose 2 distances. Moreover, the formulas are going to be simple enough to give hope for unique reconstruction of the network as well. And in fact, I was hoping this would be the theorem, but in fact, this is currently a conjecture. So you have the same kinds of hypotheses, and we're going to have to assume that all the weights are strictly positive if they aren't going into a hybrid vertex. And we're going to have a technical assumption that there aren't pseudocycles. Pseudocycles are something technical which would sort of contradict that the parents coincided in time. If you know that, I strongly suspect that if you know the tree average distance between the members of X, then n, as well as this arc length, can be uniquely determined and constructed in polynomial time. So in this particular thing, you could construct the network itself in polynomial time. So what I want to do is I want some highlights of the first proof. How do you determine the arc lengths and how simple these formulas are? That's what's to impress you. So suppose we started with this network. To start off with, you remember we know the network, we know the tree average distances. The red arcs are the ones we know the weights of, because those are 0, because those are into the hybrid vertices. Now, a normal path is a directed path that starts at the vertex, and so that every vertex after the start is a tree child. So, for example, 19, 18, 7 is normal. You start here. It doesn't matter what kind of vertex you start at, but every vertex thereafter along the path is normal. It's a tree child. But 18, 17, 16, 5 is not, because you blew it when you went through this hybrid vertex. So the important thing is that every arc on a normal path lies in NP for every parent map P, because there's a unique parent for each of those things along the way. So rule 1, consider an arc AB. I'm trying to find its weight. Suppose there's a normal path from B to Y, and Y is as a tip, from B to X, and X is in the tip, and from A to Z, and that's in the tip. Then you can find the weight by means of that formula. And really, the reason is because that's true in every tree NP, because this path, this path, this path, and this arc, they're all in every tree. Over here, the path could differ in the different trees because there might have been some hybridization along the way, but you always have the same formula that works in every 3. And so that's a pretty simple formula. And so if you look at other things, you can get all now those red arcs known. Those weights are known. Okay, so now suppose H is hybrid. And you have paths here from the parent Q1 to say X1, Q to the X2, H to Y. Then there's a nice formula given at the top. That isn't very complicated either. You need to know where just what the Y, the X1, and X2 are and the relationship there. It makes strong use of the fact that these weights going into the hybrid are 0, because you get different formulas involving these arc lengths. But if they're 0, they don't affect matters. So that means we can now get this arc length, and we can get those. Now we're still left with some things around the parents of the hybrid, around the parents of the hybrid. So here's the most interesting rule. Suppose H is hybrid, same situations, parents Q1 and Q2, these other paths, X1 and X2. Then you can get the weight of this particular arc length, from this formula. You have the distance from X1 to Y minus the distance from the root to Y plus this other combination which involves X1 and X2. That's a pretty simple formula. The idea of the proof of this is that you can make use of the idea of a complementary parent map. So if suppose you have a parent map where P of H is Q1, and you have another thing, P prime, a parent map which is exactly the same in all places except at H when it's Q2. So there's this graph, and this is a subgraph. It has NP, and then NP prime is exactly the same except this one would be replaced by that one. You look at this linear expression which is being used to get the formulas. Well, if you look at an NP, you get it's the weight of this arc minus the distance from V to Q1, which isn't very neat. But you look at the complementary P prime, the distance is the weight from Q1 to X1 plus the distance from V to Q1. That gives us an opportunity, because if you add those two things, you get twice the weight of the thing you're looking for. So there's a cancellation. You just have to add things in pairs in the right order in order to find the average. So you get this as the total weight of that arc. So now you could apply that to get, say, 17.6 arc lengths. So now what's left, there are a few black things, but then you can use the other kinds of rules to fill in, because you know the distance from, say, 18 to 6 by one of the earlier rules, because this is a normal path. So you go through that process, and you get all of them. So if the network is not normal, then the other arc lengths can often be uniquely determined. Remember, we have that matrix method. Yet the formulas are complicated, not necessarily local. So here's something that's not normal. You see you have all of these connections with several things which don't have any tree children. Well, in this particular case, the arc lengths are completely determined from the network, but you see it's a pretty complicated formula involving these distances. If you're trying to reconstruct the network, you'd have to be able to guess which of these formulas are relevant and recognize somehow that occurred. So let's go back to the conjecture. How might we go about constructing the network itself from these distances? Well, what's the status? There are lots of partial results in a working computer program. The question is whether you can prove that it works. But the idea is that there are two kinds of steps. You can use a recursive argument to reduce it to just two cases. Maybe there's a cherry, and maybe there's something else. Well, if there's a cherry, then that just means you have that situation, and we can use rule 1 to figure out what this length is, what this length is. You can remove x and y, you can figure out the distances from everything to q, and so you can throw it out. Moreover, there's a necessary and sufficient condition in terms of the tree average distance to recognize the cherry. So you can always do that. Okay? If you don't have a cherry, then you can prove that this configuration exists, in which there's a hybrid with a child. The two parents, each of them have a child, and these are all leaves. You have this situation. Well, by rule 2, you can compute this, because by rule 3, you compute those, and then you can find out what all the distances are to the disease, to any other vertex. So you can remove those. Well, those are the only two cases that can occur. You can deal with it. Why isn't this a theorem? There are really strong necessary conditions to recognize that this happens, but I don't currently have them as sufficient conditions. So as soon as those are sufficient conditions as well, then we'd have the theorem rather than conjecture. So what kinds of things might be worrying about? I guess I'm running out of time, but you're worrying about actually constructing things that satisfy that are like the tree average distance, finding more robust formulas so that the errors don't grow, dealing with other kinds of hybrids within degree 3 or higher. So I want to thank the Isaac Newton Institute, the organizers, and thank you for your attention.
Take one question, and then Mike's going to have an announcement. But any questions from the audience?
Yes.
So just a practical question to everybody this morning. Is a normal tree expected from biological data, or a normal tree is a special case?
It's certainly a special case, but of course a tree is a special case. So I
Not on Earth. I mean,
if you have a sexually reproducing species, then in fact the underlying network is very complicated. So the question is how much simplification you can occur.
so I guess my question was more, I realize it's a special case mathematically. I was wondering whether anyone had intuition as to whether, if you look at plant trees, if you look at deep phylogeny, whether normal networks are going to be common or not. I don't have an intuition as to whether they're common or not.
What I'm suspecting is that if you take a network, there are ways to modify the network to make a normal network.
Okay.
And that might be some intervening stage for doing the full analysis.
Okay, thank you.